Hello everyone. So today's topic will be logistic regression. The topics I am going to cover in this video are: the first topic is logistic regression. Under logistic regression, I will explain the sigmoid function, cost function. This is used to find the global minima. And the second topic will be the performance metrics. Under performance metrics, we will check precision, recall, F1 score, and ROC AUC. Okay. Along with this, I'm going to demonstrate the practical implementation. During the practical implementation, I will also show you how to handle the categorical columns and how to handle the imbalanced data set. So these are the topics will be covered. So if we begin with the logistic regression. What is logistic regression? Logistic regression is a machine learning algorithm. It is an ML algorithm used for binary classification. So what is the binary classification? We know that we have x1, x2, x3, the independent variables, and the dependent variable or target variable y. If our y is continuous, example salary, then it is linear regression. If our y is binary, that is 0 or 1, true or false, yes or no, customer will churn, not churn, diabetic, non-diabetic. So if the output value is only 2, either it is true or false, either it is yes or no, either it is 0 or 1. This is known as binary. So logistic regression is used for binary classification task where the output is either 0 or 1. So to deal with this, let's plot a graph how it is going to look, and I am taking a simple example where x is glucose level and y is diabetic or non diabetic. If it is 0, it is non diabetic, patient is non diabetic. If y is 1, then the patient is diabetic. So how is going to look x and y? So glucose level consider 24, 302, 57, 101, and it will be 0, 0, 1, 0, 1. So we'll get the binary has the output 0 non-diabetic and 1 has diabetic. Binary classification task. So if we plot it in the graph, it looks something like this. X glucose level and y diabetes. We have only two outputs, that is 0 or 1. If we draw a line here, it is 0 or 1. So what will be our best fit line now? It can't be like this is a wrong. It can't be like this is wrong. It can't be like this is wrong. So what will be the best fit line for the logistic regression? We have to find it. For the best fit line, to identify the best fit line, logistic regression, we use something called sigmoid function. Let me draw sigmoid function graphically. This is 0, this is z, this is sigmoid of z, and this is 0.5 and this is 1. So the sigmoid curve will be this is our sigmoid curve. It fits both for 1 and 0, where the probability is greater than or equal to 0.5 is the probability. If it is greater than or 0.5, then the sigmoid of z will be 1. If probability is less than 0.5, then sigmoid of z is equal to 0. And the equation of sigmoid function is sigmoid of z is equal to, that is 1 divided by 1 plus exponential of z. So what is z here? What is z? What is z? Z is nothing but the linear equation. Z is equal to theta naught plus theta 1 x. Theta naught is intercept, theta 1 is coefficient of x, and x is input variable. So our logistic regression equation will be logistic regression equation will be h of theta is equal to 1 divided by 1 plus exponential of minus z, where z is equal to theta naught plus theta 1 of x. So this is the equation of logistic regression. So graphically, the data, our best fit line will look like it is 0, it is 1, this is 0.5, and this will be the sigmoid curve. This is our best fit line for logistic regression. Okay. So how to get the best fit line? So what will be the equation for the best fit line? Same as the linear regression. We have to again use the cost function. Cost function to find the best fit line. So what is the cost function for logistic regression? Cost function is, here there are two terms. Why? because our output variable, target variable y is binary values, either 0 or 1. So if y equal to 1 and if y equal to 0, so cost function has two terms. So if y equal to 1, it will be minus log of h theta of x, and if y equal to 0, it will be minus log of 1 minus h theta of x. So this is our cost function. If y is equal to 1, it is minus log of h theta of x, and if y equal to 0, it will be minus log of 1 minus h theta of x. So if we combine this equation and write it, our final cost function will be minus y of log of h theta of x minus 1 minus y log of h theta, log of 1 minus h theta of x. I have added a term here, 1 minus y. We should get this equation, right? This is the cost function, and together we'll if I combine and write, it will look like this. So why I have added this term? Consider if y equal to 1, then this will be 0. 1 minus 1 is equal to 0, and 0 into anything will be 0. So our cost function will be minus y of h theta of x, right? And if y equal to 0, then this value will become 0, and our cost function will be 1 minus y, that is 0. 1 minus 0 is minus 1, minus 1 of log 1 minus h theta of x. So we get the cost function like this, and the final cost function, after combining, the final cost function will be j of theta j is equal to 1 by 2m summation of I is equal to 1 to m, sorry for that, y of log of h theta of x minus 1 minus y log of 1 minus h theta of x. Because I have not added minus term here, I will add it here. So this is our final cost function. So we know the convergence theorem, which I have explained in logistic regression, convergence algorithm, where we will repeat theta j is equal to theta j minus alpha of derivative of j of theta j with respect to theta j, which is nothing but slope. So we have to change the theta j value and apply the convergence algorithm, reach a point to find the global minima. This is theta j, this is j of theta j. The convergence algorithm, which I have explained to you in the linear regression, it repeats here. So the difference in the cost function from the linear regression to the logistic regression, and how the sigmoid curve, here we use the sigmoid function to get the sigmoid curve, which will be the best fit line, and to find the global minima for the best fit line, we use the cost function as this: j of theta j is equal to minus 1 by 2m summation of I is equal to 1 to m y log of h theta of x minus 1 minus y log of 1 minus h theta of x. And by changing the theta value, we apply the convergence algorithm to find the global minima. That's it. So this completes the mathematical institution of the logistic regression. Now I will explain you how to calculate, how to evaluate your model. What is the evaluation matrix? What is the performance matrix for classification task, for the classification algorithms in machine learning? So what is the performance matrix? Performance matrix is the methods used to evaluate the performance of the classification model, machine learning model which you have built. So the first performance matrix is confusion matrix. The confusion matrix, let's consider this as actual data and this as predicted data. This will be 1 0, this is 1 0. If actual is true, if actual is true and predicted is also true, it will be true positive. If actual is false and predicted as true, then it is false positive. If actual is true and predicted is false, then it is false positive. And if actual is also false and predicted is also false, then it is true negative. So this is the confusion matrix. Based on this confusion matrix, we will derive the formulas for accuracy, precision, recall, and F1 score. So let's start with accuracy. Accuracy is the overall performance of the model. Accuracy gives you the overall performance of the model. The formula for accuracy is true positive plus true negative divided by true positive plus false positive plus true negative plus false negative. So this is the formula for accuracy. It is the overall performance of the model. The next is precision. What is precision? Precision gives you out of all actual values, how many are correctly predicted. Let me write it. Out of all actual values, how many are correctly predicted. The formula for precision is precision equal to true positive divided by true positive plus false positive. If you see here, the precision is focusing on false positive rate. Our focus is on false positive rate. So when we have to use the precision, when we have to go for the precision, in all the machine learning models, we cannot go for the overall accuracy model. We have to specify, like we have to select precision or recall or F1 score or ROC-AUC curve. So when we have to specifically use the precision to check the accuracy of the model. Let me explain that with a scenario where a customer applies for a loan. Customer applies for a loan. That is our scenario. Okay, so what will be this scenario? Actual, predicted. Customer might be a fraud, he won't repay the loan, or customer is not fraud, he will pay the loan, he will repay the loan, he will return the loan. So our prediction will also be same, fraud, not fraud. Let's consider this scenario. At the initial stage of loan application, let me write this. At the initial stage of loan application, if the customer he's not fraud and he's applied for the loan, and the model which you have built will reject the loan application because the model has classified the customer as fraud, that is false positive, he is not fraud, but your model has classified him as false positive and rejected the application. What happens in this case? You will lose the customer, bank will lose the customer, because customer has a bad experience. Being a genuine, his loan application is rejected. So in this case, his loan application is rejected. So in this case, false positive rate is very important. What about false negative? The customer is fraud, but your model has classified him as not fraud. Even at the initial stage of application, if your model has classified the fraud customer as not fraud, but the bank has other, when he goes for the next stage of loan application, we will check his credit score, we'll ask him for the mortgage, we'll ask him for the surety, then you can process further. But in the initial stage itself, if you decline the loan application saying because your model has classified him as a fraud, then you will lose the customer. In this scenario, false positive rate is important. So the project requirement is to reduce the false positive rate. So we have to go for precision to check model accuracy. So we have to go for precision to check model accuracy. Next is recall. It is also known as sensitivity. Let's check this. What is recall? Out of all predicted values, how many are correctly predicted? Out of all predicted values, what is the formula for recall? Recall equal to true positive divided by true positive plus false negative. In precision, we have used false positive, but in recall, our focus is on false negative rate. This is false negative rate is important in recall. So what scenario, under what scenario we should choose recall to check the model accuracy? Let's consider the scenario here. Scenario of diabetes. Patient has given the basic tests to check diabetes, and your model makes predictions. let's see what prediction the model makes. Actual data, predicted data. Patient is diabetic, non-diabetic. Predicted data diabetic, non-diabetic. Our confusion matrix will look something like this. True positive, false negative, and true negative. So this is our recall now. Our recall says TP divided by true positive divided by true positive plus false negative. What happens in this case? Suppose the patient is non-diabetic. Consider first scenario 1. Actual and predicted. Actual patient is non-diabetic, but machine has predicted it as diabetic. So what will be the next process? So doctor will recommend further tests to confirm whether the patient is diabetic. Doctor will recommend further tests. It will be expensive. So patient has to just spend money here and go for further medical procedure to reassure, to confirm he is a diabetic or non-diabetic. But in scenario 2, actual data is patient is diabetic. Actually the patient is diabetic, but your machine has predicted non-diabetic. What will happen in this case, in this scenario? Patient will not get the treatment. He won't go for the further test. He won't get the treatment for the diabetes. So which has the high risk? Scenario 1, he will go for the further test, which are expensive. He will spend money. But here the patient is diabetic and it is not getting the treatment. This scenario is risky. So here the requirement will be to reduce the false negative. Patient is diabetic and machine is identifying him as non-diabetic. So in this case, false negative rate is very, very important. So the project requirement is reduce the false positive rate. In case where the false negative rate, reduce the false negative rate. Where we want to reduce the false negative rate, we should use recall to check the accuracy of the model. We should use the recall, not the precision. Based on the scenario, we should decide either we should go for precision or recall. Next is F1 score. F1 score is combination of both precision and recall, because the formula is 2 multiplied by precision into recall divided by precision plus recall. F1 score is used when you want to reduce false positive rate plus false negative rate. When you want to reduce both, should be reduced. you should go for F1 square. I have told next concept is ROC and AUC. I told you the sigmoid function, right? Here it will go from 0 to 1, and this is 0.5, where probability is greater than or equal to 0.5, y equal to 1, and probability is less than 0.5, then y is equal to 0. Logistic regression makes prediction based on this probability. So 0.5, what is 0.5 here? This 0.5, this 0.5, this is the threshold based on which machine is making predictions. So these thresholds, so for different thresholds there will be different predictions, right? So using these thresholds and the probability concept, using the threshold and the probability concept, we will plot using the probability and threshold, we will plot the ROC curve. This is false positive rate. X-axis will be false positive rate. Y-axis will be true positive rate. True positive rate. And our ROC curve will be like this. What are these points? What are these points? These points are thresholds. These points are thresholds. So if your project requirements says identify the less false positive rate where you can have the high true positive rate. So it comes here, right? Somewhere here. See, at this point, false positive rate is less and true positive rate is high. So this threshold can be used. This threshold can be used instead of 0.5, which is default. Instead of using the default threshold, you can find the threshold where your false positive rate is less and true positive rate is high. So what is AUC then? The complete area which is under this ROC curve, the complete, I will draw one more diagram, sorry for that. FPR, TPR, ROC curve, and the complete area under this curve is known as AUC, area under curve. This covers for what all the values the model is making the prediction. This is area under curve. If AUC score is near to 1, if it is near to 1, then the model is good. The model is good. It is making a good predictions. So based on the ROC-AUC curve, this is how you can identify the model accuracy. So accuracy score, precision score, recall score, F1 score, and ROC-AUC score. So these are the performance metrics we used in the classification machine learning algorithms to find the evaluation, to do the evaluation of the model. So next I will demonstrate the practical implementation where these concepts will be more clear to you. I will try to clearly explain this to you, and also some of the feature engineering like handling categorical data and handling imbalanced data. So let's start. Stay connected, stay with me. We'll try to learn as much as possible. So I have built a data diabetes prediction using logistic regression model. Here we will use certain input features and find whether the patient is diabetic or non-diabetic. First we'll begin by importing the libraries. I have imported the pandas, numpy, matplot, seaborn. Okay, the loaded the data. You can get the data. I have downloaded this data from Kaggle. I have also uploaded the data in my GitHub account. Yeah, here it is. Diabetes prediction dataset.csv. You can download the data from here. I will provide the link in the description. Okay. So see the columns here. We have the gender, age, hypertension, and all, and diabetes 0, 1. Okay. Let me give you brief description of the data. So gender is a categorical column. It has three genders: male, female, and other. Age is numerical continuous variable. It is in years. And hypertension is a binary column, 0 or 1. If it is 0, he is no hypertension. Hypertension is BP, what we call as. And 1 is hypertension. Yes, the patient has the hypertension. And heart disease, 0 has no heart disease, 1 is heart disease, is detected with heart disease. And smoking history, never, customer never smoked, or he is currently smoking, or he used to smoke. Former smoking is he used to smoke but now he has stopped. Ever, customer is a regular smoker. And not current. Not current means recently he has stopped. And no info, customer smoking status has not been provided. BMI is something which is calculated with your height and weight, like excess weight or less weight. It depends on that. Higher BMI is associated with the risk of diabetes, because if the person is like overweight, there are chances of diabetes. So these are the blood levels: HbA1c level and blood glucose level. These are related to the diabetes. These are the medical test reports. So these are two columns and they are numeric and continuous variables. And the diabetes is our target variable. It is used for we are building the model to find the diabetes target variable, while either the patient is diabetic or non-diabetic. 0 non stands for non-diabetic and 1 stands for diabetic. Okay. Df.info. Let's do the df.info. We have 10,000 entries of data, 10,000 of data and 9 columns. Totally we have 9 columns. 8 in dependent columns and 1 is target variable. Dependent column and 8 are independent columns, and 1 is target variable, that is diabetes. So now I have plotted the distribution plot to check the target variable. If you see the true, that is 0, diabetes 0, non-diabetic data is more, and the diabetic data is less from the plot. So to find out like actual count of those, I have used dot value counts. If you see, 91,500 data points belong to non-diabetic, that is 0 class, 0 non-diabetic class, and 8,500, only 8,500 out of 10,000, only 8,500 points are belong to class 1, that is diabetic. So the distribution for non-diabetic is 91.5% and diabetic is 8.5%. So this is clearly I can demonstrate this. I have also used pie chart here. I have also plotted the pie chart here, which clearly demonstrates our data is imbalanced. So we have to deal with this data. If there is imbalanced data, we have to handle this imbalanced data. So how to handle this imbalanced data? What is the process for handling imbalanced data. There are three ways. I will tell you the three ways. One is upsampling. Second is downsampling. And third one is SMOTE. These two are resampling techniques. In upsampling, so let's see here, in our data, non-diabetic. Okay, non-diabetic has more 91.5% and diabetic is 8.5%. So this is majority class and this is minority class. What happens in upsampling? Upsampling will increase the data points from minority class. It will generate the data. There is no specific rule, but it will create the duplicated records. It will make the similar kind of records. This is upsampling. And in downsampling, it will decrease the majority class. It will delete some of the data points. It will delete the data points from the majority class. So this is upsampling and downsampling technique. I used to go for SMOTE. I prefer SMOTE. What is SMOTE? Synthetic minority. O stands for oversampling technique. Synthetic minority oversampling technique. So this in general is upsampling, which means we will increase minority data points, minority class data points. And second, why I use the synthetic method? What is meaning of synthetic here? Synthetic means it will generate by interpolating. Interpolating word is important here. By interpolating between existing points. Between existing points. Synthetic data means, I will write it neatly, sorry. Why I use synthetic here is generates data by interpolating existing instances. Interpolating existing instances. SMOTE uses interpolating existing instances to generate new data. I will show you something. Okay. This is majority class. This is majority class, non-diabetic, 91.5%. And these data points are minority class, diabetic, 8.5%. So what is generating data by interpolating existing instances? What SMOTE does is, it will connect two nearest points. It will connect two nearest points and generates data on that point. It will connect two nearest points. SMOTE will connect two nearest points and generate data on that line. Again, it will connect, will connect, it will connect, will connect, connect, and it will generate new data points. So this is the logic what SMOTE uses to generate new data points. This is the way of upscaling. This is the way of upscaling done by SMOTE. So this has some logic. Data is not created randomly. So this data, the original data has variance. So the new data which is created, these green points which are created by joining the two nearest instances, will also have the variance. So I prefer SMOTE for handling imbalanced data set. Okay. So I have to use SMOTE here to handle the imbalanced data set, but I will not do it here. I will not do it here. Why? Why? Because I will do the SMOTE imbalanced data set. I will perform SMOTE on imbalanced data set after splitting the data into train and test, because I don't want the data leakage. I don't want the data leakage. That's why once you split the data, then you perform it. And next, if you see here, one more thing I have to explain here. We have two category columns: gender and smoking history. Okay, gender has three genders: male, female, and other. Smoking history has 2, 3, 6 categories: never, current, former, ever, not current, no info. So if you see these two categories, I have to convert them into numerical features, because machine learning algorithm learns on numerical features, not on categorical data. So we have to handle the categorical values. So methods I use for dealing with categorical columns are: one is nominal or one hot encoding, label and ordinal encoding. Target ordinal, I think, sorry. Target guided ordinal encoding. These are the three methods to convert the categorical data into numerical column or numerical data. So first we will start with nominal all one hot encoding. Nominal one hot encoding. So what is nominal data? Nominal data, there is, how you can define is, no natural order, no ranking. If there is no natural order or no ranking in the categorical values, then it is known as nominal data. Example, I will give you the example of department. This is my categorical column and this has values HR, finance, IT, law. These are the different departments I have. Is there any order here, like HR and finance? If there is any relation greater than or less than or equal to, we don't have any specific relation here. Every department is independent of each other. It is not related. It is not related in any ways. In such case, we have to do one hot encoding. One hot encoding. What this does is, for every categorical value, it will create a separate column. For HR, it will create one column. For finance, it will create another column. For IT and for law, it will create one column. If the value is for HR, it will put 1 here and rest all are 0. If it is IT, it will 0, 0, 0. If it is finance, it is 1, rest are 0. If it is law, it is 1 and rest are 0. Simple logic. Whichever the value is true, it will specify it as 1 and rest all are 0, 0, 0. Which is true, it is specified as 1 and rest all are 0. And create separate columns for each categorical value. Next is label and ordinal encoding. If there is order or ranking in the categorical values, the categorical column, then we have to do the label or ordinal encoding. I will explain you with the example. Let's consider the example. Size of a shirt or size of small, medium, large. See, small, medium, large. Sorry. Large is greater than medium and medium is greater than small. This has an order. So I will label this column. For the small has 0, for medium has 1, for large has 2. This is how I get converted from categorical to numerical value. We will take another example like degree. Bachelor's, master's, PhD. So this has order. So we can convert this bachelor to 0, master's to 1 and PhD to 2. This is label and ordinal. In the name itself, ordinal says there should be some order or there should be some ranking. So we can convert the categorical columns into numerical values, and it does not create a separate category column for each categorical value. Only one categorical column. It just labels it based on the order, either 0, 1, 2. It's just labels based on the order. So the last one is target guided ordinal encoding. See, what this does is, I will it will rank the, I will write it neatly. Wait. it will rank the categorical values based on the mean or median of the target value. Suppose I will write it neatly. Rank the categorical value based on mean or median of target value. Let's consider an example. Here it is, the categorical column is graduation and the target column is salary. Okay, the target column is salary. Bachelor's, master's, bachelor, PhD, again bachelor, master, PhD. Okay, so bachelor's, it is some salary, 90k, 90k, 100k. For masters it is 120k, bachelor's again 80, PhD 160. So it is like this. So what target guided ordinal encoding does is, it will for all the bachelors, for all the bachelors column, for all the bachelors categorical value, it will calculate the average. It will calculate the average of the target variable, 90 divided by 5. It will calculate the average of the target variable, and it repeats the same for again for masters, then for PhD. And based on the average, suppose we got for the bachelors the average salary, for bachelors the average salary is 80k, for masters the average salary is 120k, and for PhD his average salary is 50k. So in this, so by calculating the average salary for each categorical value, it will find an order. So bachelor has the least salary, so it will give the ranking as 0. For masters it is 1, and for PhD it is 2. This way it will convert the categorical values into the numerical values by calculating the mean or median of the target variable for each categorical value. So this is how we will encode the categorical values into numerical values. So let's get back to our practical implementation. We have two columns here. One is gender. Oh, sorry. One is gender, which has 3 categorical values: male, female, and other. And other is smoking history. And if you see both gender and smoking history, there is no order, or there is no ranking, and there is no dependency between the categorical values. So we have to go for one hot encoding, because there is no order. We will perform one hot encoding, and we will perform it only on the train data. Okay, we perform only on the train data. So first I will build a logistic regression model with the imbalanced data set so that we can compare the performance. Compare the performance. So I have split the data x and y. X is our independent features. So I will drop diabetes column, and y is only the dependent variable, target variable, that is diabetes. I have also made a list of numerical features here, list of categorical features here. I have differentiated them, which I will use it in the later part of the code. So after splitting into x and y, I have to split the data into train and test. X train, X test, Y train, and Y test. So I have split it in X, Y. Test size is 0.2, which is 20% of the data will be test data and 80% of the data will be training data. Random state is 42. And what is stratify equal to Y? I have specified stratify, which data I have to stratify, that is Y, that is diabetes data. Why the diabetes data has to be stratified? That means I have imbalanced data, right? So I don't want the X trend to have all the columns which are non-diabetic, and Y train or y test column to have all the rows which are diabetic. I want the equal split of both the diabetic and non-diabetic between Y train and Y test, so that the model trains well. So I have used here stratify equal to Y. It will equally split the output variable. It will equally split the target variable between Y train and Y test. You can see here Y train 0.15, 0.91, that is 91% is 0, class label is 0, non-diabetic, and 8%, 8.5%, 0.085 is 1. It is same with the test data. The proportion, the ratio of 0 is to 1, non-diabetic is to diabetic, is same for both Y train and Y test, which is achieved by specifying stratify equal to Y. This is important. So once after splitting the data, now I want to make the transformation, that is imbalanced data. I have imbalanced data, so I have to handle it, and also I have to want to convert the categorical features into numerical features, which I will do only on my training data. Okay, my training data. How I will do it? I have written a simple program here. Column transformer is used to apply multiple pre-processing techniques on multiple columns. So I have made a list here. This is just a name, num and cat. This is for numerical features. What process you have to do the scaling, scale the numerical features, okay, which I have splitted here. See, I have made two lists, right? Numerical features and categorical features. So for numerical features, do the standard scaling, and for the categorical features, do the one hot encoding. So I have defined here one hot encoder. So both the standard scalar and one hot encoding are imported from skitlearn library, skitlearn library. So after specifying this function, I have to apply it. I have applied on the X train processed, as I have specified it as X train process is equal to preprocessor. Preprocessor is nothing but the function which I have created here, preprocessor. Preprocessor dot fit transform X train. We have to do only the fit transform on X train, and for test data we have to do only the transform, because we don't want the data leakage. So we want to just fit transform the values, and here we have to fit the values. Here the mean is equal to 0 and standard deviation equal to 1. We have to scale the values. So our X train data and X test data, numerical features will be scaled, and categorical columns will be converted to one hot encoding. Next, I have built the logistic regression model. I hope this is clearly visible. Logistic regression is important from sklearn dot linear models. Here I have defined the logistic regression model. Log reg equal to logistic regression of random state is again 42, which has to randomly select the samples, and max iterator is 1000. Because I have large data set like 10,000 of records, I don't want to train my model at a time with 10,000 records. I don't want to train it. My train consists 80% train data, that is 8,000 records. So I don't want to train 8,000 records at the same time. So what I will do is specifies max iter is equal to 1000. So only at a point only 1000 records will be given to the machine. So machine trains on first 1000 records, then second 1000 records, then third 1000 records. So machine trains 8 times and the learning will be better. After defining the model, I have fitted it with the X train processed and Y train. Okay, the logistic regression model is built. So see, I have made the predictions here. Y predict is equal to dot predict X test processed. So let's check the performance matrix based on the prediction. That is what we do, right? Y test is actual data, Y test, and Y predict is predicted data from the confusion matrix, which I have shown you, predicted versus actual. So if you see here, I have plotted the confusion matrix. This is important here, confusion matrix. Is a bit you need to understand it. I will explain you how this confusion matrix has been plotted, because in theory I have shown you the predict. Let me explain you. See, in theory I have shown you this is actual, right? This is actual data and this is predicted data. This is predicted and this is actual. But when we plot, when we do the practical implementation, here it is interchanged. Predicted is here and actual is here, and the values also it's 0 1 and it is 0 1. These values are also interchanged. So this has, you have to understand this confusion matrix, how this is looking. What is the true positive here, what is the false positive here? Let me show you. So this is predicted and this is actual, and data points are also changed, right? This is 0, this is 1, this is 1 and this is 0. 0 is non-diabetic, 1 is diabetic. 1 is diabetic, non-diabetic. Then what is our true positive? This will be, this will be our true positive. This is our false positive. This is false negative. And this is true negative. Yeah, right. So this is our confusion matrix now. You see the practical implementation and see the theoretical concepts, and if you draw the confusion matrix, it is looking like this. Okay. So this is the confusion matrix, and we have plotted, we have calculated the precision recall. This is the classification report. So precision score, see here, precision score is 0.86. You should go for the 1, you should not go for the 0. You should go for 1. Why 1? Why not 0? See, this is 1, this is 1, right? So you have to go for this true positive. What is the precision formula? Precision equal to true positive plus true positive divided by true positive plus false positive. So we are checking whether the patient is diabetic. We have to focus on the diabetes. So we have to go for this. We have to check these values. So precision score is 0.86. Okay, precision score is good. And recall score is 0.62. That means 62% accurate. And F1 score is 72% accuracy. And overall accuracy of the model is 96%. Okay. This is the logistic regression model with imbalanced data set. Now I will apply the SMOTE to get the balanced data. See, IMBLR, this is the model library from which we have to import the oversampling, which is SMOTE. And I have defined SMOTE here, and then I have fitted the only the train data, not the test data, to avoid the data leakage. To avoid the data leakage, I have fitted, I have transformed, I have applied the SMOTE only on the train data set, X train, Y train, SMOTE dot fit, again X train and Y train. So now if you do the value count, see, this is Y train before the SMOTE. There are 73,000 records of 0 and 6,800 records of 1. Now after applying the SMOTE, that is Y train SMOTE is equal distribution of 0 and 1. 73,000 records of 1, 73,200 records of 0. So now I have the balanced data. So let me train this balanced data for the logistic regression. Let me fit it. Same, we will repeat the step, but here we don't use the X train. We'll use X train SMOTE and Y train SMOTE. Once we fit the data, and again I will do the confusion matrix. This is our false positive 2131, right? This is true positive, this is false positive, and this is true false negative. So if you compare, see, with the imbalanced data, first of all, what for the diabetes we should focus on recall. For the diabetes data, I have explained you the scenario here. Recall data scenario I have explained here. We have to focus on false negative. We have to go for the diabetic kind of data set. For health data set, we should also always focus to decrease the false negative rate, because we don't want to identify the patient who is diabetic as a non-diabetic and put him at the risk. We should focus on the false negative. So our goal is to reduce the false negative rate and increase the recall accuracy. We should increase the recall accuracy. If you see here, this the value here is 644. This is logistic regression base model without with the imbalanced data set, without the SMOTE. I have not balanced the data set. It is imbalanced data set. I have the false negative rate as 644. And if you see here, after applying the SMOTE, this is for after applying the SMOTE, if you see the confusion matrix, from 644 it has decreased to 187. It has decreased to 187. So our false negative rate has decreased. If you see, it has decreased. from 644 to 187. It has decreased from 644 to 187. False negative rate has decreased. That means recall accuracy has increased. Recall accuracy has increased. Let's check the recall accuracy. See, for the previous model, the recall accuracy was 62%. 62%. Now the recall accuracy is 89%. Recall accuracy has increased because I have balanced the data. From 62%, recall accuracy has increased from 62% to 89%. There is increase in the recall accuracy. That means our model has improved. Got it? See, precision has decreased and F1 score has decreased, but our focus is on recall. So recall accuracy has increased. So this is how we built the logistic regression model. For the understanding of ROC, ROC is not recommended here because we are focusing on recall. Just for the understanding how the ROC looks and how you have to use the ROC-AUC, I have also applied it. I have also demonstrated it. See, what I am doing is I am making the probability predictions, right? I have told you it is based on probabilities. So calculating the probabilities, using those probabilities, I have used the threshold and plotted the ROC-AUC score. It is 0.96. That means it is near to 1, 96%. It is a good accuracy. Model is performing good. And if you plot the ROC curve, it will look like this. See, it is away from the line. It has covered maximum area. That means AUC and area under curve is high. So the model is making good predictions. It is covering all the data points. This is false, x-axis is false positive and true positive. So if I want to identify the threshold where my accuracy is true positive rate is more and false positive rate is less, then see at this point, right, somewhere here the false positive rate is less and true positive rate is high. So this can be my new threshold. My basic threshold is 0.5, but this can be my new threshold. So let's plot it with the threshold. The code you can get it from ChatGPT. That's not an issue. I have also provided the code in the GitHub. Let's plot it. See, if you see here 0.69, 0.1, the false positive rate is low and true positive rate is high for 0.61. If your project requirement says your precision score should be high, you have to decrease the false positive rate, then you can go for this. You can identify the threshold by using the ROC. See, I have changed here now. Now I will make the predictions on my new threshold 0.6. I have changed my threshold from 0.5 to 0.6 and I plotted the confusion matrix. The accuracy is increased. You can make like that. You can identify the threshold from that. The false positive rate has decreased here. Here false positive rate, if I change the threshold for 0.5, when my threshold was 0.5, the false positive rate was 2131, and when I changed it to 0.6, I changed my threshold to 0.6, see 0.6, and I plotted the confusion matrix. False positive rate has decreased to 554. So if you want to decrease the false positive rate, you can use the ROC curve and identify the new threshold where the false positive rate is less and true positive rate is high. Okay, that's all for this video. I hope you have understood the logistic regression, mathematical concepts, and practical implementation. I will also provide the GitHub link in the description, where you can download the notebook if you want a brief understanding of the code and also the data set and build your own model. You can also do the hyperparameter tuning. It gives you an opportunity, it gives you sufficient things for the logistic regression. I hope this video is good. We'll meet in the next video. Thank you so much for watching my video. Thanks a lot.